Right now, beneath your feet, water is quietly expanding by roughly 9% in volume.
Which, doesn't sound like a lot at first.
Right, it really doesn't sound like a world-ending number. But when you realize that that 9% expansion is happening when the water is trapped underground, well,
Yeah.
it generates enough upward and outward pressure to literally snap a solid concrete highway in half.
Yeah, it's staggering. It's an immense amount of force.
Welcome to this deep dive, everyone. Today, we are unpacking a really fascinating battle. We're looking at how structures actually manage to survive an extremely cold, frost-prone climate.
And it's definitely a battle.
Oh, absolutely. So our mission for you today is to explore this. We've got a great stack of sources, including some incredibly detailed engineering breakdowns and diagnostic matrices from DIY retaining wall. And we're going to figure out why traditional brute force construction just fails so spectacularly against the winter Earth.
Right, and we'll get into why a specific, completely counterintuitive type of structure called the segmental retaining wall, or SRW, is basically the ultimate cold weather survivor.
Exactly. Okay, let's just unpack this. We're talking about heavy engineering here, but really the core of this whole discussion comes down to a philosophical shift, doesn't it?
It really does, yeah.
Right.
It's a shift away from that very human instinct to just dominate an environment. It's moving toward the realization that flexibility almost always outlasts rigid strength.
I love that.
Yeah, I mean, historically, when we build things, if nature pushes hard, our immediate instinct is just to build something harder, something heavier and stiffer to block it.
Just throw more concrete at it.
Right. Exactly. But when you try to fight the freezing Earth in a head-to-head brute force battle,
Yeah.
the Earth is going to win every single time. So to survive extreme cold, you actually have to stop fighting the winter and start adapting to it.
I want to dig into that adaptation for sure. But before we can understand how these walls survive, we really need to define the enemy for you listening. We have to understand the immense cyclical power of freezing soil.
Right. What engineers call the frost engine.
The frost engine, such a cool name. And the underlying equation for this is pretty simple at first glance, right? It's just water plus freeze equals movement.
Simple enough, yeah.
But the sources talk about this phenomenon driving it called the ice lens. And this is where the physics get, honestly, genuinely mind-blowing to me.
Oh, it's fascinating.
Because it's not just that groundwater freezes once and expands 9%, it's actively growing over time, right?
Exactly. Most people picture the ground freezing the same way. Like an ice cube freezes in a tray in your freezer, it turns solid, it expands slightly, and then that's it. It's done.
Right, that's what I always thought.
But an ice lens in the soil is incredibly dynamic. Because of the specific thermodynamic properties of soil and water, that initial tiny layer of freezing ice creates this powerful pressure differential, and that triggers capillary action.
Let's actually pause there and break down capillary action for a second, because it's so crucial to why this engine is so destructive. So how is the water physically moving toward the ice?
Okay, so think of it like dipping the very corner of a dry paper towel into a spill on your counter.
Okay.
The water quickly climbs up the paper tile, right? Just
Yeah.
totally defies gravity. And that happens because the water molecules are attracted to the microscopic spaces in the paper.
Oh, wow.
Well, soil acts the exact same way. It's just full of tiny microscopic pore spaces. So when an ice lens forms, the freezing process creates this suction effect. It uses those microscopic pores to actively draw in unfrozen liquid groundwater from below.
So it's not just freezing, it's literally pulling water upward against gravity directly toward the freezing zone.
Precisely. The ice lens isn't just sitting there frozen, it's actively drinking.
That is wild.
It is. It continuously pulls in new moisture, freezes it, and grows thicker and thicker. And this creates a compounding upward and outward pressure against, whatever structure happens to be buried in the ground right above it.
So it's like a freezing subterranean sponge that actively drinks more water just to swell up and punch your wall.
That's a great way to put it.
Okay, so engineers crack this as a relentless four-step cycle. First, you get the winter freeze, where those ice lenses form, they start drinking, and they expand.
Right.
Second is the wall heave. That's where that tremendous compounded pressure pushes the ground up and outwards against the structure.
Yeah, that's step two.
Then third is the spring thaw, where the ice finally melts, leaving behind these massive voids, and the displaced soil settles completely unevenly.
Which is incredibly damaging.
Right. And finally, step four, the wall deforms. You get rotation, tilting, or massive separation cracks. And then winter rolls around and it just happens all over again.
Yeah. It is literally a machine that never stops.
So If this pressure is that relentless, how do we usually try to stop it? Do we just build thicker walls?
For a very long time, yes.
Yeah.
That's exactly what we did. What's fascinating here is that the default human response to the frost engine has always been that brute force approach.
Just make it heavier.
Right. Which brings us to the traditional cast-in-place, or CIP, concrete retaining wall. The strategy behind a CIP wall is incredibly straightforward. You just eliminate movement entirely, period.
Okay, so how does it do that?
Well, the design relies on a massive, highly rigid, vertical concrete stem. And that stem is supported by an enormous, continuous concrete footing that is trenched really deep down into the earth.
Right, the goal being to get that footing way below the frost line.
Exactly.
Oh, wait, let me play devil's advocate here. Let's say I go out, I rent an excavator, and I dig a massive trench completely below the frost depth.
Okay.
And I pour thousands of pounds of concrete so deep that it's completely underneath the layer of soil that actually freezes. So the frost can't grab the bottom of the wall to heave it upward. Why doesn't that just solve the problem entirely?
I mean, it sounds like it should work perfectly,
Right.
but it's actually a deeply flawed strategy because it only addresses vertical lift. It completely ignores the horizontal threat.
Oh, interesting.
Yeah, if we break down why that approach fails in the real world, the first issue is just execution. If your footing is even slightly too shallow, or, if you get an unusually brutal winter that drives the frost line deeper than it has been in a century.
Which happens.
All the time.
Yeah.
If that happens, you get footing uplift. The frost heaves, it lifts just one single corner of that massive concrete base, and because the whole structure is one rigid piece, well, it cracks the entire wall.
Yikes. Okay.
But let's assume your footing is perfectly deep. Let's say you've won the vertical battle. You are still completely vulnerable to lateral frost pressure.
Okay, so what exactly is lateral frost pressure?
That is the pressure coming from directly behind the wall.
Ah.
You've protected the bottom from lifting, sure,
Uh-huh.
but the entire back of the vertical wall is still in direct contact with the soil you're trying to hold back.
Right.
So if water gets trapped in the soil behind that wall and freezes, the resulting ice lenses extend horizontally. They push outward against the vertical face of the wall with thousands and thousands of pounds of force.
But concrete is incredibly strong. Why can't a foot-thick concrete wall just, take the hit?
Because concrete is strong in compression, but it is incredibly weak in tension.
Okay, what does that mean in practice?
Well, if you put a heavy weight on top of a concrete block, so you're compressing it, it can hold massive amounts of weight. But if you try to stretch or bend concrete, its tensile strength is virtually zero.
Wow. Really?
Yeah, think of it like a piece of blackboard chalk. You can press the ends together really hard and it won't break. But the second you try to bend it in the middle, it snaps instantly.
Oh, that makes total sense.
Right. A rigid concrete wall does not tolerate horizontal movement. It does not bend. So when lateral frost pressure pushes against it, it suffers a brittle, catastrophic fracture. It just snaps like a twig.
That is a wild image. A massive, heavily engineered concrete monolith completely shattering just because it couldn't bend a fraction of an inch to absorb the blow.
Exactly. If we connect this to the bigger picture, fighting nature with rigid resistance is just a losing game. Because when frost wins, it wins big.
So, if being rigid guarantees a snapped wall, what is the alternative?
The alternative is a complete 180-degree turn in our engineering philosophy. According to the structural diagnostic matrix in our sources, instead of resisting the movement, you design a system to accommodate the movement.
Accommodate it. Thinking about this, it reminds me of the evolution of medieval armor.
Oh, how so?
Well, the traditional cast-in-place concrete wall is kind of like a solid, thick breastplate of steel armor. It feels invincible. But if a warhammer hits it hard enough, the metal completely caves in or shatters and it's ruined.
Right.
But the segmental retaining wall, the SRW we're talking about, is like a highly engineered sheet of chainmail armor. It's composed of all these individual interlocking links. So when it gets hit by the frost heave, it shifts, it adapts, it sort of rolls with the punches, and then it settles right back into place without actually breaking.
I love that analogy. That's a highly accurate way to visualize it.
Here's where it gets really interesting for you listening. The secret to strength here is actually bending.
It really is. Unlike a solid, brittle mass that snaps under lateral pressure, these unbonded SRW block systems absorb the micromovements caused by the freeze-thaw cycle without taking structural damage. The frost heave pushes, the chainmail flexes slightly, and then during the spring thaw, it settles right back.
That's brilliant. Let's actually build this chainmail wall from the ground up for the listener,
Yeah.
because understanding the anatomy of an SRW really highlights how clever this is.
Good.
Starting from the very bottom, the foundation. We just established that traditional walls need massive concrete footings trenched way below the frost line, but the SRW throws that rule out entirely, right?
Completely. There is no deep concrete footing.
Instead, it uses a shallow, well-compacted granular base. Wait, so you're telling me we were replacing a massive concrete anchor with a shallow trench of loose gravel? That sounds way weaker.
I know it sounds weaker, but physically it's vastly superior against frost. And by granular base, we mean clean, crushed stone. The reason this works is all about voids and water retention. Native soils, especially ones heavy in clay or silt, they hold tightly onto water. But clean, crushed stone has these large void spaces between the jagged rocks.
So the water just flows right through it.
Exactly. Water drains straight through it. And if the water drains away, there is no water left to freeze. You are literally starving the frost engine of its fuel.
Oh, wow. That's so smart.
And furthermore, frost can't grab and lift a bed of crushed stone the way it grabs a solid slab of concrete. There's nothing for it to latch onto.
Ah, I see. So you're swapping a brittle anchor that can be snapped for a draining cushion that neutralizes the threat entirely.
Precisely.
Now, I know there's a caveat here from the sources. The depth of that gravel pad isn't just a random guess. The thickness of the gravel leveling pad actually scales to the frost depth, right?
Yes, that's a crucial point.
So if you are building in an incredibly cold climate on soils that hold a lot of water, you dig a deeper gravel pad to provide more drainage and a deeper buffer. But you are still completely avoiding a rigid concrete monolith.
Exactly right. You scale the cushion, not the anchor.
Okay, so the base is secure and it's draining. What about the soil resting directly behind the wall? If that soil is full of water, we still get lateral frost pressure, right?
Right, which is why the anatomy of an SRW mandates specific backfill material. You don't just dump the muddy clay, you excavate it right back behind the wall.
You definitely don't want to do that.
No. You must backfill the immediate zone behind the blocks with more clean, angular stone. Again, this creates a free draining zone. You are actively moving water away from the back of the wall, basically short-circuiting the equation before the water can freeze and push outward.
All right, here's the part of this engineering that I have a really hard time wrapping my head around. The actual wall structure itself. The blocks.
That's the chainmail.
Right.
Yeah.
If you look at the cross-section of an SRW, you have these heavy concrete blocks stacked on top of each other. But there is no mortar. There is no cement. They are completely unbonded. So let me get this straight for the listener. We are intentionally not gluing these blocks together. You're telling me that a wall meant to hold back potentially hundreds of tons of earth isn't glued together in any way.
That's exactly what I'm calling.
How does that not just instantly bulge outward and collapse the second the dirt pushes against it? We want them to wiggle a little bit during the season.
Yes. It is incredibly counterintuitive, but those unbonded blocks are the very definition of the chainmail analogy you brought up earlier. Not gluing them is a deliberate design choice.
Okay, explain that.
It creates what we call planned system flexibility points. If the ground shifts slightly due to a harsh freeze, a rigid glued wall cracks. But an unbonded SRW block is designed to tilt a fraction of a degree. It slightly yields to the pressure.
But what stops it from yielding too far and tumbling down the hill?
Two things. First, the blocks have interlocking features. Usually these are built-in concrete lips or fiberglass pins that lock the rows together vertically.
Okay, so they can wiggle, but they can't easily slide completely forward off the row below them.
Exactly. And second, and far more importantly, is gravity and the angle of the wall. SRWs are typically built with a slight backwards lean or a batter into the hill.
Oh, I've noticed that. They always slope back a little.
Yeah. So when the frost heave subsides in the spring, gravity pulls that heavy block right back down into its locked, aligned position.
It's basically structural judo. It absorbs the energy instead of blocking it.
That's a great way to put it.
But even with the backwards lean and the pins, I mean, just a stack of loose blocks and a column of gravel can't hold back a massive hillside on its own. The dirt would eventually overwhelm the dead weight of the blocks, wouldn't it? There has to be something anchoring the face of the wall to the earth behind it.
And there is. This brings us to the absolute magic ingredient of modern retaining walls, the reinforced soil mass, which is created using something called geogrid.
Okay, this is a high-tensile synthetic mesh, right?
Yes. Think of it like a heavy-duty, highly engineered plastic lattice. It basically looks like a net. During construction, You lay this mesh horizontally on top of a row of blocks, and you unroll it deeply into the soil area behind the wall. Then you stack the next row of blocks right on top of it, pinching the front of the net between the heavy concrete.
Okay.
And finally, you dump your crushed stone and soil directly on top of the net behind the wall.
So how does a plastic net physically stop the wall from falling over?
It's all about friction. That mesh has specific sized holes or apertures in it. When you dump heavy crushed stone on top of the geogrid and compact it, those jagged stones fall through the holes in the mesh and lock into place.
Oh, they get stuck in the net.
Exactly. They become trapped. This creates immense friction. The stone can't move because it's caught in the grid, and the grid can't pull forward because it's buried under tons of locked-in stone.
Oh, wow. So instead of the wall acting as a dam trying to hold back a river of dirt, the geogrid actually sews the dirt and the wall together.
Precisely.
It turns the loose soil behind the wall into a single, unified, heavy block of earth. The dirt is literally holding itself back.
That's exactly it. The geogrid transfers the load and distributes the stress evenly across a massive area. The granular soil, the gravel, the unbonded blocks, the geogrid bit, they are no longer separate pieces. They are acting cooperatively as one flexible, incredibly heavy mass.
Okay, so the design is just brilliant on paper. The physics of the chainmail make perfect sense. But if someone is actually out there putting a shovel in the dirt to build this, how does it go wrong?
Oh, it can go wrong in a lot of ways if you aren't careful.
Let's walk through the actual chronological process of building one of these walls in a cold climate. Because execution is where theory meets reality. When you first break ground and dig your base trench, what is the biggest mistake you can make before you even lay a stone?
The fastest way to guarantee failure is building on frozen or unstable native soils.
Okay.
If you dig a trench in December, say, and the bottom of your trench is frozen solid, and you build your wall on top of it, you have essentially built on a temporary foundation.
Because it's going to melt.
Right. When spring arrives and that deep subsoil finally thaws, it's going to consolidate. It will settle unevenly, and your beautifully engineered, flexible wall will sink, warp, and deform. You must always excavate down to stable, unfrozen ground.
That makes a lot of sense. So let's say we hit good, unfrozen dirt. Now we pour our granular base, our crushed gravel. I see a lot of people just dump the gravel, maybe smack it a few times with the back of a shovel and call it a day. But proper compaction is critical here, right?
It is non-negotiable.
Yeah.
We talked earlier about how the jagged edges of the crushed stone need to lock together to create a stable cushion.
Right, the friction.
Exactly. If you don't properly compact that stone with heavy machinery, you leave excessive voids, empty pockets of air between the rocks.
Which is bad.
Very bad. Over time, the massive weight of the wall above will crush those loose rocks together, the voids will collapse, and the wall will sag. Or worse, those excessive voids fill with water, and suddenly your draining cushion becomes a bathtub, restarting the frost engine. Yeah, you have to lock those particles together tightly. And frankly, you shouldn't just guess by how it feels. Proper engineering requires actual density testing to verify that the compaction meets the standard.
Okay, so the base is perfectly compacted. As we start stacking our unbonded blocks and backfilling with clean stone, we have to consider where all the water we are draining is actually going to go. We need internal drainage routing.
Right. It's not enough to just let the water fall through the gravel. You have to actively direct it out and away from the base of the wall using perforated pipes.
The Ultimate Guide to Internal SRW Retaining Wall Drainage talks a lot about this.
It does. And this isn't a one-size-fits-all solution either. You have to customize your drainage routing based on the specific topography of the site. If a massive slope is funneling hundreds of gallons of rainwater directly at the back of your wall, your drainage system has to be designed to handle that specific volume.
That makes perfect sense. Now, as we are building the lower rows of the wall, there is a concept the sources highlight called proper embedment. We don't just start stacking the very first row of blocks at the grass level so we can see the whole wall, do we?
Absolutely not. You have to bury a portion of the bottom of the wall underground. This is called embedment.
Okay, why?
Think of the wall like a lever. The dirt near the top of the wall is pushing outward, trying to tip the wall over, which simultaneously tries to kick the bottom blocks sliding forward. By burying the bottom courses of blocks securely underground, you lock the base in place and physically prevent that kick out from happening.
How do you know how much block to actually bury?
It is a highly specific calculation. It depends entirely on the soil type, the total height of the wall, and whether there's a slope at the bottom or the top.
So you shouldn't just guess.
No. It's so critical to the geometry of the wall that professional resources, like DIY retaining wall, they provide specific tools, things like a free embedment calculator spreadsheet, to map out exactly how deep your embedment needs to be based on your site's variables. You really do not leave embedment to guesswork.
Okay, to the listener, definitely check out those tools to ensure you don't leave this to chance. And as we continue building up, laying our geogrid, stacking our blocks, we're constantly backfilling. And again, just to reiterate, we are exclusively using that granular, clean stone. We are not using frost-susceptible clay.
Correct. You have to ruthlessly protect that drainage zone. Non-frost susceptible materials only.
Finally, what if I'm actively building this wall? I have my trench open, my soil is exposed, and the weather report says a massive cold front is coming in overnight.
You have to take aggressive winter precautions. An open excavation is incredibly vulnerable. If you expose the deep subgrade and leave it open to a hard overnight freeze, you have essentially allowed frost to penetrate far deeper into the earth than it naturally would have under the insulating layer of topsoil.
Oh, wow.
Yeah, you have to cover the exposed work areas, you use thermal blankets, and you actively manage the temperature of the soil during the construction phase to ensure you aren't accidentally freezing your own foundation before you build on it.
That is a lot to juggle.
It is. Honestly, considering all these compounding variables, from soil types to compaction physics to embedment mathematics, this is an area where consulting with professional engineering services, like the ones from DIY Retaining Wall for site-specific winter design support, is just incredibly smart.
It's super clear that a brilliant design concept still requires flawless physical execution. If you cut corners on compaction or you use the wrong dirt for backfill, you are just handing the advantage right back to the freezing earth.
Exactly.
So to recap the journey we've taken today, we started deep underground, looking at the horrifying reality of the frost engine. Capillary action, pulling water against gravity, ice lenses drinking and swelling, generating thousands of pounds of upward and outward pressure.
A truly destructive force.
We explored how trying to stubbornly resist that force with massive, rigid, cast-in-place concrete walls is a recipe for a snapped, catastrophic failure because concrete simply can't bend.
Right.
The true cold-weather survivor is the segmental retaining wall. It survives by doing the exact opposite of brute force. It uses crushed stone to drain water away, starving the ice lenses. It utilizes geogrid to weave the earth and the structure into one heavy, unified mass. And most importantly, its unbonded blocks function like chainmail, gracefully accommodating the earth's movements without breaking.
It really is a profound paradigm shift, moving from rigid resistance to adaptive management.
It really is.
And there is a broader context here that makes understanding this engineering more critical now than perhaps ever before.
Oh, definitely.
If we look at the reality of climate change, the environments we are building in are shifting rapidly. We aren't just getting one long, predictable deep freeze a year anymore. In many regions, winters are becoming much more erratic.
Right, the cycles are changing?
Exactly. We are seeing...
That is such a powerful thought to end on, the undeniable strength of the chainmail over the brittle rock. To you, the listener, thank you so much for joining us on this deep dive. Keep questioning the structures around you, keep your eyes open for those hidden ice lenses, and most importantly, stay curious. Catch you next time.